Hello everyone, welcome to my channel. Today's video is question number 4, 2015. Let's read the question first. Let GCD-AB represent the greatest common divisor. GCD, greatest common divisor, of the two positive integers a and b. For example, GCD 18 and 45 equals to 9, since 9 is the greatest positive integer that divides both 18 and 55. The function Pn is defined to equal to the sum of the n greatest common divisors, GCD 1n, GCD 2n, and so on, and so on. Then GCD nn, for example, P6 equals to GCD 16 plus GCD 26 plus GCD 36 plus GCD 46 plus GCD 56 plus GCD 66 is equal to GCD 16 is 1, GCD 26 is 2, GCD 36 is 3, GCD 46 is 2, GCD 56 is 1, GCD 66 is 6. So P6 equals to 15. Note, you may use the fact that P A multiply B equals to P A multiply PB for all positive integers A and B with GCD AB equals to 1. Okay, let's see part A. What is the value of P125? 125 equals to 5 to the power of 3. 125 has factors 1, 5, 25, 125. So GCD n 125 has 4 possible values. And GCD 5, 125 equals to 5. GCD 10, 105 equals to 5. Is GCD 1, 125 equals to 1. GCD 25, GCD 50, 125 equals to 25. GCD 125, 125 equals to 125. So let's see the table. Yeah, there are 4 possible values of GCD n 125. And for this value, there's only one n. There are 4 n's, and there are 20 n's. 125 divide 5 equals to 25, but 25 you need to minus 1 and minus 4, that's 20. Okay, so the left are all this. So we add them up, that is 1 times 100, 5 times 20, 25 times 4, 125 times 1 equals to 425. Okay, let's see part B. If R and S are different prime numbers, prove that P R squared multiply S equals to R multiply 3R minus 2 multiply 2S minus 1. That since RS are both prime numbers, so GCD R squared and S equals to 1. So we can use the given fact that PAB equals to PA multiply PB, PR squared S equals to PR squared multiply PS. Let's see PR square first. Let's see PR square first. There are three possible GCD values, which is 1, R, and R square. R square only 1, which is R square. R is R to R, and so on. And R minus R, there are R minus 1, because it can't be R square, because R square we used here. So R minus 1, and for this one, it left R square. There are R square numbers from 1 to R square, and R square minus this, so this is, and we get PR square equals to R square times 1, R times R minus 1, and this is times 1. So we simplify it, we get R multiply 3R minus 2. So PR square equals to R multiply 3I minus 2. Now we see PS. Since S is a prime number, there are only two possibilities of GCD and S. It's 1 and S. So there are 1 and S minus 1. And let's explain it. Because PS equals to GCD1S plus GCD2S plus GCDS minus 1S plus GCDS S, which GCDSS is S, and these are all equals to 1. So this is 1 times S minus 1 plus S plus this S. So we get S plus S. Okay. Now we get this proved. Yeah, this one multiply this one. Okay. Remember we use this fact in part B. Okay, let's see part C. If R and S are different prime numbers, prove that P R square S can never be equal to a power of a prime number. That is, can never equal to T to the square to the power of n. T to the power of n for some prime number T and positive integer n. Okay, let's assume that P R square S can equal to T to the power of n. Each of the factors must be powers of T. That means R must be powers of T. 3R minus 2 must be powers of T. 2S minus 1 must be powers of T. Okay, that which means R can divide powers of T. Because R is a prime number, T is a prime number. That means R equals to T. Let's see the second factor, 3R minus 2. 3R minus 2, since R is a prime number, 3R minus 2 is greater than 1, means R can divide 3R minus 2. So let's try. 3R minus 2 divide R equals to 3 minus 2 over r equals to r powers of t. Since r equals to t, so it's powers of r. It's an integer. It's an integer. So r must be 2. If r is other prime numbers, this one cannot be an integer. This one cannot be an integer. So r must be 2. Since t equals to r to the power of n means 2 to the power of n. But 2s minus 1 is odd. It's odd, and since r equals to 2, s is a different prime number. So s is greater or equal to 3. That means 2s minus 1 is greater than 1. 2s minus 1 is odd, and it's greater than 1, so it cannot be 2. Powers of 2. Cannot be powers of 2. This contradicts our original assumption, which 2s minus 1 must be powers of 2. So that means p r square s can never be equal to a power of a prime number. Okay, let's see part D. Determine with justification two positive numbers m for which pm equals to 243. Okay, 243. We see that 243, okay. 243 equals to 243 equals to 3 to the power of 5. Okay, here's a simple table for P1, P2, P3, P5, P7. Let's consider if m equals to s. S is a prime number. Means m is a prime number. So ps equals to 2s minus 1. S is a prime number, which s is a prime number. Yeah, because for prime numbers, we got ps equals to 2s minus 1. It's in the part B. We already know that. So 243 equals to 2s minus 1. S equals to 122. It's not a prime number. So m is not a prime number. Okay, let's try m equals to rs, which rs are prime numbers. Means p rs equals to pr multiply ps. pr multiply ps equals to 243. That means either it's 3 multiply 81 or 27 multiply 9. There are only two possibilities. There are only two possible multiplies. Okay, we already let's see the table. We already prepared this table, which is P2 equals to 3 and P41 equals to 2s minus 1 equals to 81. So m equals to 41 times 2, which is 82. Okay, let's see. Is that possible? M equals to r squared times s. It's not possible because 243 is a powers of t, powers of prime number. It must be powers of prime number. But we have already shown that r squared s, p r squared s cannot be a power of prime number. So this is not possible. Let's see this possibility. M equals to r cubed times s, which means Pm equals to Pr cubed times Ps equals to 243. Okay, let's calculate the Pr cubed. Pr cubed equals to this. There are only one. Yeah, we've already done that. Actually, the part A is a r cubed. So you can check the answer with part A. So we got this. Pr cubed equals to 4r cubed minus 3r squared, which is r squared, and multiply 4r minus 3. So Pr cubed s equals to this r squared multiply 4r minus 3 multiply 2s minus 1 equals to 243. So r equals to 3 and 4r minus 3 equals to 9. 2s minus 1 equals to 3, which s equals to 2. So m equals to r cubed times s, which is 54. So we get two positive integers. M equals to 82 and m equals to 54. Both satisfy. Pm equals to 243. And I will leave a challenge to you that why m cannot be something like r, s, and t. There are three different prime numbers. Which let's see, if m equals to r, s, t, pm equals to pr, ps, pt. So let's try the smallest three like this, and we see the table. Yeah, there are 5. It's impossible because we need 3, the powers of 3, and there are 13. It's impossible, and it's surely greater than 200. See, 3 times 9 times 13, which is greater than 243. Even the smallest prime numbers, 3 of them, the production is P. The P production is more than 243. That means it's not possible. Okay, thank you very much. Persistence is most valuable. Thank you very much. See you. Bye bye.